But I started my journey here at an instruments class sponsored by the National Centre for Atmospheric Science in Scotland, and my topic was on latent heat. So this was actually geared for beginning graduate students, and I'm not going to make you go through all of that, but nevertheless, I think it provides a nice counterpoint to what we've been focused on, which is a lot of dry dynamics, right? So if we really want to do atmospheric models, we're going to have to take into account the effects of moisture. And so the question here is, does the energy that drives hurricanes also heat your beer? Here's a sample beer that somehow became corrupted in this file just moments ago. And this is done with another professor at UW, Dargan Frierson, and also Stella Choi and Stephen Bray, a couple undergraduates who assisted in the measurements. We're going to tell you how it really works. So a few fun things about, a few fun things about moisture. This is water. The two hydrogens on each molecule are the blue, the red is the oxygen. The question is this ice or liquid water? Any ideas? Well, we have a vote for ice. Any votes for liquid water? We have a vote for liquid water. Vote for ice. Again, you can see are the molecules, the red oxygen and the two blue hydrogens. The black lines are the molecular bonds, the covalent bonds, and the white lines are these hydrogen bonds that hold the molecules together. You can see the white lines periodically breaking and reforming. This, in fact, is water. You have to break some of the story is ice is a situation where every oxygen links to four other hydrogens. Two are part of the molecule, two are bonded by the hydrogen bond. And so all of the little white bonds that are possible would be made and fixed in ice, or at least only breaking for a short period of time very randomly. So this is ice, and so an interesting question here, and this is, I hope we can develop some intuition about this whole subject by thinking about some simple facts. What percentage of the ice crystal bonds are broken in liquid water at 0C? So we know ice has essentially none of the bonds broken. We have to put some energy into the ice to turn it into water, and we break some of these bonds. And so I just want you to think, so imagine, I'm going to go through 10%, 20%, 30%, 40%, 50%, 60%, just round numbers. Think of who would vote for 10% of the bonds are broken to make water? 20, 30, 40, 50, 60, 70. Okay, I'm not trying to hold, I just want you to think about the number, okay? So the story is 12 to 15 is all you need to break to get from the solid to the liquid. We'll come back to that in a moment. And of course, again, if we're boiling water on the stove, we know that the water temperature does not change as you add more heat. Our recipes do not require us to monitor the temperature of boiling water. Instead, and so if you were students, I'd make you answer, right? But I don't want to insult you. So we know that the heat is going into the energy required to break these intermolecular bonds, latent heat. And in fact, it turns out you can get a pretty good estimate of what other results suggest are the number of bonds that need to break to convert ice to water by comparing the latent heat of fusion, the work you do to convert the ice to water at 0C, to the total amount of work you'd have to do to convert ice to vapor, which is going to involve adding both the bond breakage from ice to water and then from water to vapor. So if you add up the latent heat of fusion and condensation at 0C, and divide that into the latent heat of fusion, you get 0.12, which goes back to this idea that apparently about 12 to 15% of the bonds are broken at 0C when you convert ice to water. Okay, so not a lot to make that flow. Okay, then we get into the strength of latent heat. This comes in again to this idea of why dry dynamics could be missing some of the picture, and we all know that, and I'm also on this same gravy train if we're not going to be worrying too much about moisture, but still it doesn't hurt to think about this. So if we ask ourselves what's the ratio of the energy needed to boil away a glass of water that's already at 100 C compared to the amount of energy required to raise the water in the glass by 100 C, say from freezing to boiling, that turns out to be a relatively big number too, and I won't make you guess. But it's 540 calories per gram is the latent heat of vaporization at boiling. And of course, it takes 100 calories to raise 1 gram of water from 0 to 100 C. So 5.4 times as much energy is required to boil this stuff away as is required to bring it from freezing to boiling. So again, the latent heat of fusion, evaporation is very big. In fact, the latent heat of fusion is considerably smaller in comparison, but still hardly trivial. So it's a big effect. And along these same lines, again, trying to deal with human examples, steam burns are very nasty. And we don't really have to deal with steam burns too much in the modern world. We don't have that many steam engines, I guess. But yes, if you do not open your radiator cap, for example. If your car boils over, you never open your radiator cap. So if we ask a similar question, what's the ratio of heat absorbed cooling a gram of steam from, say, 100 C to 50 C, with the notion that once the gram of water is at 50 C on your skin, you're not too distressed anymore. What's the ratio of that to the heat absorbed when you simply cool a gram of boiling water down to 50 C? So we have the numbers from last time. This is our most complicated mathematical equation, so please note here at the Newton Institute that this is anyway. So 540 calories per gram plus 50 calories to absorb heat as we...
Only one digit, or is that the exact number?
You know, it could well be that that's the exact number, because we got a lot of, kind of nice numbers here. Yeah, it is exact. Right? We can do this on our heads. It is exact. So it's bit reproducible. Okay. Anyway, so the point is, it's a fact. There's 12 times more energy supplied to your skin when you get blasted by that gram of steam than just a gram of boiling water. Latent heat is powerful. Okay, so global energy balance. The Earth's surface is heated by radiation and cooled in part by upward fluxes of sensible and latent heat. So again, we can ask, in the globally average sense, what's the ratio of the latent heat flux to the sensible heat flux at the surface of the Earth? On the global average, the story is that the latent heat flux is over 3 times as big as the sensible heat flux. A big effect. All these moist processes are, well, it's dominating the sensible heat flux, for example, the latent heat flux. That is the amount of heat that's removed when we evaporate water from the oceans or when plants do evapotranspiration and send moisture into the atmosphere. That's 3 times as big as the heat we carry upward just by thermals. Okay, I'm going to actually skip over this, I think, because it involves stuff that's too technical. We don't want to hear about this, probably, presumably. So let's just go by all this stuff. But the point is that, well, I will come to this one. The bottom line is a typical rising air parcel rising from the surface. Here's a condition where it's 27 degrees C at the surface temperature and 18 degrees C dew point. If you lift that air up, it turns out that by the time you lift it, if you were to lift it undilute, which never happens, if you were to lift it undilute, the extra warming it would experience relative to if you'd been dry and lifted exactly the same undilute way, turns out to be a difference of over 20 C, right? So you've warmed the parcel 20 C by the condensation of moisture in that rising air parcel, which helps to fuel thunderstorms. That's not 20 degrees C relative to the environment, it's just relative to no moisture being present in the parcel. Okay, so let's get on to the main question that you're all here to understand, I hope, which is how does latent heat affect your cold drink? So when you're trying to explain science to non-scientists, it's nice to have examples that they can relate to in their own experience. And when we talk about latent heat, we all talk about how we get cooled by the effects of latent heat. We sweat, the sweat evaporates, it cools our bodies. If you've gotten out of the water someplace and it's a windy day, you cool off a lot faster than if there's no wind because the evaporation is faster. So we're used to the idea that our body supplies heat to evaporate water, but we need a situation, if we want to talk about what goes on in these clouds, we want a situation where condensation occurs and releases heat, which is what goes on in the thunderstorms, and is what potentially happens when you get sweat or you get water condensing on the outside of your cold drink, right? So there's at least potential for there to be heating of your drink by the atmosphere when water condenses on the outside of your drink. And so I thought about this. If you don't, well, yeah, you have to, well, yes. Or if you don't live, for that matter, in some place where it's too cold and you can't get much moisture out of the atmosphere. But there's at least potential.
You don't worry about your cold.
Yeah. There's lots of places, yeah, that's right, where you want to warm your drink up, even if it's a beer. Well, okay, there are those places where, but we're going to assume, let's skip that. Okay, so anyway, so after thinking about this, the first thing, what I actually asked these students to do is to develop an experiment to estimate the effect of latent heat on a can of beer, to think about the instrumentation involved, But of course, the first thing you would do before you did anything is a back of the envelope calculation, right? I mean, is this just a totally ridiculous idea? You can actually get some sort of obvious temperature change in a can of beer out on a hot, muggy day due to latent heat being deposited on the outside of the can. So here's our back of the envelope calculation. Suppose a 12-ounce can, of course in the US we have 12-ounce cans, sorry about that over here, but near 0C is covered with 1/10 of a millimeter film of condensed water. So pretty thin film.
It isn't centigrade though.
Oh yes, you mean, yeah, well, we're still scientists now and then in the US. Not all the time, especially not when we get too political. But anyway, suppose a 12-ounce can near freezing, well, actually, the fact it's near freezing is a little bit unimportant until later. But anyway, is covered with this amount of condensed. In fact, I don't think I really want it near freezing because it's going to be close to freezing the water. But anyway, let's just suppose, so just delete that. And imagine we have taken our can out of the refrigerator. It's pretty cold, but not necessarily that near 0C. Oh, who cares? Anyway, if all the latent heat of condensation that makes up this 1/10 of a millimeter thick film is transferred to the drink, what's the change in its temperature? That's a calculation you can do pretty easily. We start by calculating the surface area of the can. It's roughly 286 centimeters squared. So that means if we have a 1/10 of a millimeter thick water layer, there's 2.86 grams of water condensing. The heat released then is going to be this 2.86 grams times latent heat near zero. Actually, this is where this comes in. So this is the latent heat near 0C, a little bit above 0C. The latent heat is a function of temperature. It's 1,710 calories. So now the temperature rise is going to be our 1,710 calories divided by the content of our can, which a 12-ounce can is 340 grams. It's 5 degrees C. It's a huge effect, right? I mean, I was shocked when I got this number, and I had to have several people check it, just because I had a hard time believing that a little thin film of water on the outside of your can can produce a 5 degrees C rise, right? So okay, so now we have a back of the envelope calculation that suggests this could be an interesting thing. Yes?
So what's the time scale? Like how long would that take in comparison to if the temperature is 25 and the normal heating of it?
Right, excellent question. So we need to get to the bottom of this, right? So all this says, and that's a good point, say, okay, you know, if we could do this, subject to this assumption, we could get a 5 degrees C rise. But does that really happen? I mean, at least there's something that could be important here. But I mean, what if it's 3 times as thick a layer, for example? Then we've got 15 C, right? So what's going on? There's at least that mass, that large mass of liquid inside the can, in fact, is not so great that it could not be heated potentially by some condensation. So we get on to testing this. Okay, so that's our back of the envelope calculation. Those of you who are skeptical, and there were a lot of people skeptical about this, let me tell you. Actually, I should tell you how I really tested this first. Dargan Frierson and I, it's not on the slides, Dargan Frierson and I went down in his downstairs bathroom while his wife was out of town. And we heated it up with a space heater, really hot, and we put some cans out and checked the temperature in the can and the rate at which the temperature rose in the can. Then we opened the door to his shower and we turned the shower on. So he had the whole thing just as wet as you could imagine down there in his basement, and did the same test. We got a much more rapid rise in temperature when it was wet. So that's fine, but that's not quite good enough, right? Especially if we want to ultimately publish our results, talking about what you've done.
You're saying drink your beer quicker in Houston than Colorado.
That is one of the, yeah, that is definitely the thing. So here's our apparatus, which I'd like to think is older than me, but may not be. We found this after trying a couple different strategies. We unearthed this environmental chamber in the basement of our building in the Atmospheric Science Department at UW. What we've got here, I'm going to zoom in on parts, but we have an environmental chamber that we've tricked out specially for our purposes. We have a moisture source that is a flask on a hot burner with a little tube that goes in and supplies moisture. And on over here we have a scale with a can of actually water in it that has a little removable top. We'll get to that in a moment. We're weighing this thing when it comes out. It's got a little, well, we'll zoom in. Okay, so here's our moisture source. We turn the burner on. We pump moisture in. Here's the weighing thing. The chamber's opened up. We'll zoom in over here in a minute. This is Stella, who is using very, very good posture to gently set the can on the sensitive scale. The can has this little cup underneath it to capture any condensate that drips down it. And then what we have here is this thing you can buy on Amazon.com that snaps on the top of your can so you can reclose it. But instead we stuck a stopper in there with a thermometer. And so one more thing. So here's the chamber itself. It has a series of plastic strips hanging down so that when we open it up to put the can in or take the can out, we don't change the air in the chamber all that easily. We slide in between the strips. Can sitting over here. We have instruments in the chamber to measure relative humidity. We actually had thermistors we were trying to stick in the can for a while, but we decided that the simplest strategy for us was the following. We would start a series of runs at a given temperature in the chamber with the chamber as dry as possible. We would slowly increase the humidity in the chamber and get a whole series of runs as the humidity went up and we kept the temperature constant. The way we did this is we took these cans out of an ice water bath, dried them off, shook them, took their temperature after shaking to mix just in case there was some stratification in the ice water bath, put them in there for 5 minutes, pulled them back out. When we pulled them out, the first place they went was back on the scale to weigh the condensate. Then we shook them again to mix up any stratification, and we read the temperature on the way out too. So that's how we did the whole thing. So here are the results. For 25C, the change, what we have is relative humidity in the different experiments, and the change in temperature in degrees C on this axis, and some of our later lines will be darker colors, so that'll be good. But this first curve is a linear least squares fit, more sophisticated mathematics, to the actual data points, which are these little stars, and this shows the change in temperature in 5 minutes in the liquid in the can. So we see the temperature, of course, is changing by some sort of amount just due to sensible heat transfer. And then I'll explain everything sort of synergistically after talking about this next curve. These open circles are the latent heat associated with the weight of moisture the can picked up. So remember, we're weighing the can, so we know how much water the can picked up. We convert that into heating by multiplying by the latent heat and plot that, and that's these circles. And this dashed line is the linear least squares fit to these circles. So there's several satisfying things in this plot. One is that these two lines are parallel. So what's that suggest, that these two lines are parallel? It suggests, sorry?
Correlation.
Well, there's definitely a correlation, that's for sure. There's a correlation that suggests that the sensible heat transfer is basically independent of the relative humidity. It's this much, right? So we're basically getting, that's my own stupid thing. We're basically getting about 3.5 degrees or so of warming of the can due simply to the fact we stuck the can in warm air at 25C and it started at 0C. So that's the sensible heat transfer. But that we add to that progressively more and more total heating as the relative humidity goes up, right? And so in our most moist case, we got about 4 degrees C. That is this height here of heating from the condensation in the can. So that's nice. That kind of fits our earlier example. And notice also that in this most moist case, about 88 relative humidity, 86, we're getting more heating in that first 5 minutes from condensation in the can than from sensible heat transfer. Right? So it's all kind of nice. We're happy. But of course, what are we going to do next? 25C is pretty cold, right? As we warm up the atmosphere, there's a lot more water. If you're down in the deep tropics, it's only 25 degrees C. Something's odd on the particular day you're there, right? So we were looking for more. We want to amp this up. So, here's 30. We've done a series of simulations. At 30, we get more heating just due to sensible heat transfer. We're now a little bit above 4 degrees due to sensible heat transfer. And we get a lot more heating due to the latent heating, right? Up here, we can see that we're getting latent heating now. Well, I guess it's actually in the order of 5C. Approaching 6C. These lines are still parallel. That's nice. And if we go to 35, we get more latent heat. Lines are still parallel. Sensible heating has gone up a bit too because it's warmer, but it's only about 5C now. Whereas the
You're at 35 degrees and 90 or 100% humidity. You got a lot bigger troubles than you drink.
But you still want to drink something.
Do you want to drink something for sure? Well, we'll get to so. World record dew point. Anybody know what the world record dew point is, which is relevant to this? Anybody know where the world record dew point is? That's something that's already a little high. It's obvious actually it's not really, it might not be in the tropics, as a matter of fact. It's near the Red Sea. The Red Sea is quite hot and so there's a lot of evaporation. Of course, it's right at the Red Sea. It's not in the middle of the desert, where it's certainly not going to get a world record relative humidity. I'll get to the value in a minute. That was just kind of to add tension to the talk. Anyway, so now we'll go all the way up to 40. And our sensible heating's gone up a little bit again, but the latent heating has gotten up quite a bit. In these cases here, which are 90% relative humidity at 40 C, we're getting, in our first 5 minutes, we're getting, I can't hold that level, but we're getting about 11 degrees of heating, I guess, from the condensation. So it's blasting a lot of heat into our can.
Can I ask, how is it that the heat is only going into the can and not, is that already controlled for?
Well, so
Or I mean, or you're not assuming that, you're just looking at.
we're just observing what happened, right? Okay, so I think the real story is when we do condense onto the can, aluminum's a good conductor and the can is very thin. So if we want to extrapolate this to a glass jar or bottle, we still have pretty good heat conduction in the bottle, but we have more mass in the bottle, and the mass of the aluminum can is negligible. So the only other way to carry it away is through the air itself somehow. And it doesn't seem to be happening. In other words, it seems like if you look what's going on here, there's nothing inconsistent with the idea that the two effects just add together. So I think it is basically going to the can, but we don't really have an exact energy budget in some volume around the can.
Right, it's the aluminum probably that's just transferring most of it.
Yeah, right. Okay, so now back to where do we get unrealistic? The world record dew point is 35 C, so you're not going to have these cases. But the last one, which was at 35, all of this is potentially relevant, and even at 40 C, which of course the world record dew point was not set when the actual temperature was 35 C either. So it is probably more relevant to saying, we're somewhere in here where you're going to maximize your latent heating. But still, in the first 5 minutes, you're talking about 8 degrees C of heating to the condensation in your beer can. Okay. So latent heating is powerful. This is just some stuff, right? But anyway, thanks. I hope you can now entertain yourself by having some beer, and I don't think we're going to have too much condensation on your. Well, I don't think you're going to have a can of beer to start with, but it's not here in the UK. But anyway, you can do a lot of heating of that can of beer from condensation, and up to 50% of the energy that warms it during the first 5 minutes could come from condensation on the outside. Quite counterintuitively to my mind, but nevertheless, that's the case. Questions, comments? I'm sorry I don't have beer here.
So these beer cooler things are good. Like these kind of like sleeves you put over it.
Right, and in fact we thought about doing this series with those things. We finally decided, look, let's just let it be. But I think the story is that they probably do a lot by reducing the moisture that comes into contact with the beer can, as much as is inside the sensible heat. Yeah.
So it says that the conductivity of the can is really one critical parameter.
Well, yeah, although it's got to go somewhere. So it's either going to have to, if it stays on the outside of the vessel, then maybe you can drive some sort of other current. But that would start, as you warm the outside, the reason these curves cut off what they did is because what starts to happen at, actually this is not the best example, but what starts to happen is you start to get the outside of the can being above the dew point. So nothing happens. So if you were to keep the heat on the outside, you'd stop getting condensation too. So as long as you're still getting condensation in some sense, it's got to be going somewhere. Sorry.
Just coming back to the relevance for what we're doing here, we've always felt strongly that for particularly testing non-hydrostatic models, it's essential to test cases with latent heating, because as you've shown here, it's a large energy source, and with convective instability, it's the smallest scales that are the most unstable. And so if you have a situation where air is being brought to the condensation level and it's convectively unstable, you're going to be putting in large amounts of energy right near the grid scale. And this this really stresses the numerics. So many of our test cases, like flow over mountains and this and that, at the end of the day, so much of the energy is in well-resolved scales. And so this is really a good acid test of testing the numerics where you're most interested. In other words, at getting close to the grid scale where you're trying to get the most for your money in a numerical scheme.
Right. Certainly true. Yes, it's powerful.
That's about it.
So, do numerical schemes typically do well, or?
They typically show lots of problems you never imagined existed. At least that's been my experience, that I've played with numerical schemes that look very nice in dry tests, and you get to simulating convection, and all hell breaks loose that you didn't see before, or maybe didn't expect. And because it's so effective in really testing the higher wave number end of your behavior.
But I mean, I guess my question was more about the accurately, I mean, maybe it's all sort of coupled together, but, the ability to predict how much latent heat is released. I mean, and then the feedback, I guess,
Well,
of that
but
into the dynamics.
But I mean, if you got rising air, okay, there's an equilibrium level where it gets saturated. And when you go beyond saturation, everything that's above that saturation level is going to condense. So you can actually do a pretty good job of the amount of condensation, the amount of latent heating can be pretty well represented.
Right, it's just
Provided you get
dynamics.
the motions correct, because if we are down close to the numerical resolution, either the implicit or explicit numerical dissipation stuff starts to decrease the buoyancy of the updraft, and things don't go up as far as they're supposed to, maybe, or any number of issues.
And lots of, depending on how you handle or how you do the moist numerics, you'd like at the end of your time step to be right back exactly at saturation. At least if you're in a situation, say with rising air where you're condensing. But a lot of schemes just forward project the fields, and you end up and you're not right at saturation. Or if you only do your microphysics once every now and then you get out of balance with the condensation.
Okay, time for a lab? Okay, great.
Yeah, Friday afternoon, the speaker should provide beer.
But we're in England here. The beer is
That's
warm
right.
anyway.
The beer's warm. The beer's warm, the air's cold, and it's thin.
Too much humidity in England.
What's the rate at which
drink
it
it
warms
warm
up the atmosphere?
But if it was 35°C, you might know what the beer quantity is warm.
Well, they're just more sensible. They make it warm straight away. You don't have to worry about it.
Yeah, there you go.
Moving fast.